This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. All right, so we are in the March 21st attendance ticket. Please give me a green check when you've got it ready to go. I've got 10 green checks and 48 of you, so I'm going to wait for a few more. Let me know that you're able to open it, that it's working for you. Looking good. Awesome. Yes, no social media in the chat box. Cool. All right, everyone. So there are 8 days left of quarter number 3. It is ending very, very soon. Like, that should definitely make you feel excited or maybe even a little bit nervous because it's coming up fast. Today we are starting our last unit. After this unit, there's only the final exam. So again, ending very soon. So today we're going to start talking about our unit, electricity and magnetism. Tomorrow, keep in mind that instead of doing the 9B lab, we've switched it to the 9C quiz because remember, I have a doctor's appointment tomorrow, so I won't actually be able to do my live sessions. That being said, do you still have live sessions for your other classes tomorrow? Tell me in the chat box, do we still have live sessions for other classes? Yes, you do. It's not a day off. And do you still have an assignment for me tomorrow? Even though I won't be here, do you still have an assignment? Yes, you do. There is going to be a recording uploaded, so you will have an assignment tomorrow. Don't forget that. Cool. All right, everyone. So today is the 21st, tomorrow's the 22nd, and then, yes, we have spring break. Make sure you catch up on spring break because as soon as you come back, there will only be 7 days left, and then courses are closing and courses are ending, and you won't be able to submit anything else after that time. So electricity, this unit, we're going to talk about electricity, magnetism, how they are related. We're going to also talk a little bit about circuits, and we will be building a motor for our lab, so you will see that on the Tuesday when you come back from break. Okay. Awesome. Okay, so today we should be able to identify and describe various types of electricity, define electricity, magnetism, and current, and provide examples of how electricity and magnetism affect energy. All right, so let's go ahead and jump into it. So remember, everyone, that all matter is made of atoms. Remember, atoms are the smallest complete unit of matter. And remember that what they look like, you can see down here, this is an atom. It's got a positive nucleus in the center, and then surrounding it, it's got a bunch of these negatively charged electrons. Now, those negatively charged electrons are small but mighty. They are extremely important. Stephen, just give your whiteboard a few moments to load. It might just take a little bit of time. All right, hi Mia, hi Matt. So the reason they are so important is because electrons are involved in electricity. So electricity is the flow or motion. Down here on the left. You're funny, Fat. So electricity is the flow or motion of electric charge, right? So electrons being able to move is what gives us electricity. So for example, when you see lightning or when you see light being emitted from atoms, that is due to electrons going from a high state of energy to a lower state of energy, releasing light. Okay, so electricity, very, very important. This is number 1 in your ticket. Electricity is the flow, F-L-O-W. Take 30 seconds. Give me a green check when you have that saved. Go, go, go. All right, need a few more green checks. Waiting on Addie, Alex, Amir, Junie, Angie, Tony. Let's see here. Ashley, Ashton, Ben, Sierra, Davion, D, Grant, Jacob, Josiah, Jay, Carrie, Shay, Mason, Morgan, Nia, Noah, Ruben, Sarah, Serenity, and Sid and Valerie. Go ahead, give me a green check when you have number 1 saved, and we're moving on in 5 seconds. Here we go. All right, everyone. So how many of you have ever done this? How many of you have ever rubbed your socks? So you're wearing socks and then you shuffle them across the carpet and then you go up to your little sibling and you touch them. And what happens when you try to touch your little sibling after you have been rubbing your socks on the ground? Yes, yes. It's a lot of fun because it allows you to shock them. Exactly. Zzz. Yep. So this is what is called static electricity. Now, static electricity, take a look at these first 3 letters. Remind me again, does the word static mean that it stays in place or that it's in motion? When we talk about the word static. Yeah, it works with socks. Or you know those like plastic chairs that you used to sit in at school and stuff? If you had a shirt on, you could rub your shirt against the plastic chair and then you could shock someone. Or if you ever like go down a slide, as soon as you go back to climb up it and there's that metal railing, you shock yourself. Yes, exactly. Okay, sorry. So again, static, does this mean it stays in place or does it mean it's in motion? Tell me in the chat box. And we're take a look at those first 3 letters in static. That should give us a hint. Does static electricity stay in place or is it in motion? Yeah, it stays in place, right? Static looks like the word stay, right? So it stays in place. All right, so static electricity means it's electricity that's kind of stuck in one spot. All right, so right, we just talked about how there's electricity that's in motion, but static electricity is not. It's motionless electric charges that are not being transmitted or moved by a conductor, something that carries electricity, okay? Now this happens when an object either gives up or gains electricity. Remember, electrons are negatively charged. So if you're giving up negative charges, do you think you become more positive or more negative? If you're giving up negativity, do you think you become more positive or more negative? Tell me in the chat box. Something that gives up electrons. Yeah, it's going to actually become more positive. And on the other hand, what happens if you're gaining electrons? What happens to your charge if you're gaining electrons? What do you become? More? Yes, you become more negative. Exactly. Remember, electrons are negatively charged, so it's kind of the opposite of what you expect to happen. Jeremiah. All right, so for example, oops, gotta grab this. All right, so for example, how many of you have ever done this? You grab a balloon, rub it against your hair. Yes, and you get a wonderful hairstyle, right? You can actually see, right? It starts to lift your hair up. Woo! So this is a great example of static electricity. What's basically happening here is the balloon is stealing electrons from my hair. And so this one's becoming negatively charged and my hair is becoming positively charged. But the positive charges for me don't matter very much because I'm what's called grounded, right? So I'm actually standing on the ground. So so my charges don't matter quite as much as the balloon. The balloon's charges are much more, it's affecting it much more, okay? So again, you can see, all right, the balloon becomes charged and then it can attract my hair. But the other thing is the balloon can actually attract more than just my hair. So let's take a look at this example. This is a pretty cool one if I can get it all set up. Ow. Here we go. All right, so here we go. Let's say I've got a stream of water. This is really fun to do at home if you have a balloon and if you have a faucet. You can do a small stream from your faucet. But normally, what does a stream of water do? What are you seeing here? Normally, what does a stream of water do? Tell me in the chat box. The faucet, the water from your faucet, which direction does it go? Not a trick question. Yeah, it goes straight down, right? Okay, now what I want you to notice is what happens when I put a balloon next to it. No, there's a cup here. Good question, though. All right, so now although I am going to move my keyboard back a little bit. All right, here we go. All right, so now what we're going to watch is we're going to actually watch what happens when I put a balloon next to the stream. All right, so watch this. What do you see happening? Sorry, hold on. My balloon is kind of wet, so it's having issues. Let's try that again. I'm going to get as much charge on it as possible. All right, let's take a look at this. So watch the stream of water. All right, and now watch what happens as I put a balloon next to it. Can you guys see that? I know it's a little bit hard to see. Let's see. All right, so watch this. All right, so you can see stream of water. Is the stream of water still going straight down? It's going straight down. No, what's happening here? Again, I'll show you again. Yeah, it's actually curving. Uh-oh, lost my balloon. Hold on. Yeah, it actually curves which way? Towards or away from the balloon? Towards or away from the balloon? I'll go ahead and show you again. All right, so watch here. Where is it going? No, it's actually going towards. Again, I know it's a little bit hard to see, but it is actually going towards the balloon. It would be easier to see if I actually had a consistent stream of water from a faucet. So you should definitely do it at home because it's pretty awesome to look at, but it's actually going towards it. So here's the thing. Not only does the balloon attract your hair, but it can also attract other things like water, which is pretty cool to think about. So what happens is it like bends this way and then goes away from it. So it's just hard to see because it's hard for me to hold steady and the balloon. But the whole idea is you should think of the fact that static electricity can affect water, which is kind of crazy to think about because you're like, water's not is not electrically charged. What's going on there? Give me a smiley face if you're starting to understand that static electricity is really interesting, has a really cool phenomenon that goes on with it, and we're going to dig into that a little bit later. Cool. All right. So that being said, electricity and magnetism are actually related to each other. This is why we actually learn them at the same time. So the reason they're related to each other is because they both have to do with electrons. So electricity kind of makes sense, right? Electricity is due to unbalanced electric charges, right? If you have less electrons, you become more positive. If you have more electrons, you become more negative, right? So for example, we'll learn a lot about this next quarter when we're in chemistry. But for example, if an atom loses an electron, right, it becomes positive. Gains an electron, it becomes negative. So that makes sense, right? That's electricity. However, we're also going to see that magnets are also going to be using electricity. So the crazy thing about this is that electric charges, okay, they're going to have an electric field around them. Okay, but electric fields or electric charges can actually also experience a force if they're next to a magnetic field. So that's kind of crazy to think about because we're going to see today that electricity and magnetism are very interrelated. So if you do something with one, it's actually going to affect the other. Give me a thumbs up if that's starting to make sense. Okay, we're going to see lots of examples today, but one example is when an electric charge moves through a magnetic field, it actually gets moved by that magnetic field. The magnetic field moves an electric charge. All right, this is number 2 in your ticket. Give me a green check when you have that saved. You have 30 seconds. Ready, set, go. All right, we are waiting on Addie, Alex, Amir, Tony, Ashley, Ashton, Ben, Cassandra, Sierra A, Dion D, Grant, Josiah, Cami, Carrie, Kian, Malcolm, Shay, Mason, Mia, Morgan, Nia, Nina, Noah, Ruben, Sarah, Serenity. Green checks, please, if we've got number 2 saved. Moving on in 5 seconds. All right, here we go. Yeah. All right, so here we go. Again, magnets are very related to electricity. And the reason, again, is because it has to do with this idea of electrons. So magnets are any substance that produce a magnetic field, okay? But the thing here is that magnetic fields are due to how electrons are inside of a magnet, okay? So we'll talk about this a little bit later, but if you were to zoom into what's going on inside of a magnet, you would see that electrons are spinning in a certain direction, and if electrons are all spinning in the same direction, they become magnetic. Okay, so again, electrons are extremely important. Even though they're very tiny, they're extremely important. Flowing electrons creates electricity, spinning electrons creates magnetism. This is why the two are interconnected to each other and can affect each other. Give me a smiley face if that makes sense. Smiley face if you understand. Awesome. Okay, so what I want you guys to take a look at here is that if you take a look at these 2 diagrams here, there's something really important, a really important concept that you hear a lot in physics, and that is that likes repel and opposites attract. So you can see that up here, that like charges, if you have 2 positives or 2 negatives, they're going to repel from each other. And the same thing is true with magnets, because again, magnets are just the other side of the coin to electricity. So magnets, if you have north and north pole, they're going to repel, or if you have a south and south pole, they're going to repel. The only time they attract is if it's opposites. So for electricity, if it's a positive negative charge, for magnets, if it's a north and south pole. Okay, so magnets have north poles and south poles, and their strength is greatest at the poles. Okay, so if you take a look here, for example, where you usually hear the word north and south is actually with the earth. All right, so we think of the earth as having north and south pole. So what I want you guys to take a look at here, so I'm going to go ahead and actually show you a magnet. All right, oops, grab that. All right, give me a smiley face, guys, if you can see my magnet here. It doesn't settle very easily. But you should notice that north is more towards me. It'll eventually be pointing towards me. Yeah, it's a compass, exactly. Okay, what I want you guys to notice here is that I actually have a magnet here. Okay, so what I'm going to go ahead and do is I'm going to actually put one side of the magnet here. And you'll notice that which part of the magnet is of the compass is attracted to my magnet. The north pole, which is the red one, or the south pole, which is the not red side. Which one is attracted to my magnet currently? Yeah, the south pole, right? So I can go ahead and this is the south pole right here of our compass, attracted to this part of our magnet. So what does that mean this pole of the magnet must be? If this is the south pole and opposites attract, what must this magnet be here on this edge? What must this one right here be if they're opposites? So this one's a south pole. What must this one be? Tell me in the chat box. This one's south. This one is what if they're opposites? Yeah, this one's actually a north pole. Now watch what happens when I flip it. All right, and now you can see what's attracted to the magnet now. I flipped the magnet, now which pole is attracted to it? The north pole, exactly. And this one right here, all right, this one right here must therefore be what? If north is attracted to this one, then they must be opposites. So this must be the what pole of my magnet? Yeah, the south pole. Now, what I want you guys to think about, okay, is this should kind of blow your mind here, okay, is that the north pole of my magnet is pointing towards the north pole of the Earth. But does that actually make sense? Should north be attracted to north? If the north pole of my compass is pointing towards the northern part of the Earth, does that make sense? Do opposite or do the same? Do likes attract? Do likes attract? No. So here's what I want you guys to think about. All right, if I have a magnet, all right, that is attracted towards north, the northern part of the Earth, what magnetic charge does this part of our Earth actually have? If the northern part of a magnet is attracted to the northern part of the Earth, what magnetic charge does this pole actually have? Tell me in the chat box. Take a look on the whiteboard. All right. What must this charge actually, or what must this magnetic field actually be? If north is attracted upwards, what part is this part of our Earth? Is it actually a north pole or a south pole? Yeah, so actually, physical north of the Earth is actually magnetic south. Okay, so even though this is physically north, all right, this is actually magnetic south. Give me a smiley face if that makes sense. Okay, so the northern part of a magnet is attracted to physical north only because physical north is actually magnetically south. They're actually flip-flopped. Same thing with the bottom here. What must the bottom of our Earth actually be magnetically? Magnetically, what must the bottom of our Earth actually be? Yeah, magnetic north, right? So this is physically south, but magnetically north. Give me a smiley face if that makes sense, if you understand. All right, it's kind of crazy to think about. In order for the North Pole to point north, it actually means that the Earth's North Pole is magnetic south. Crazy. Okay. Now, what I want you guys to go ahead and look at is I'm going to go ahead and show you a video. How many of you guys have seen this before, like on a movie, for example? Maybe in real life. I've never seen it in real life, but what movie have you guys seen this in? I think it's a Disney movie, isn't it? Happy Feet, yeah. I was thinking of what's the one with the bear? I feel like, yeah, Brother Bear. There you go. Exactly. Cool. All right, I'm gonna go ahead and show you a video of this. I'm gonna go ahead and tell you how this is related to our topic in a few moments, but go ahead and actually watch this first. Okay? Here we go. screen checks? Yeah, isn't that awesome looking? All right, so this is actually related to our topic today. So this is called the Northern Lights or the Aurora Borealis. All right, and so the reason that this happens is actually due to magnetism. All right, well, it's actually due to electrons and magnetism. All right. Yeah, exactly. They are the Northern Lights. Isn't that awesome? It's very mesmerizing. It's so beautiful. So what's actually happening here is that within our atmosphere, okay, we have air molecules, we have electrons, we have ions, and we also have a magnetic field going on. And when all of those things mix together perfectly, I don't know. That's a good question, Levi. When all of those things mix up perfectly, what ends up happening is that the molecules, the electrons within the molecules begin to get excited. And so as they get more and more energy, they get excited. And then what happens to happen is they have to drop back down in energy level. Remember, we actually saw that at the beginning of our video here, right? That electrons will get excited, and then when they jump back down, what do they release? What did I tell you at the beginning of class? When they jump back down, what do they release? Tell me in the chat box. What do they release? When electrons jump back down, the electrons release electrons? No. No, that not, well, it does happen in lightning, but no, specifically they release what? It happens in lightning, but specifically what part of the lightning is it releasing? No, not atoms. And the electron jumps back down, and what comes out of it? What's the first part of the word lightning? Yes, it creates light, exactly. So what's happening here, all right, is that as these electrons get excited and jump back down, they release light, and that light is what we see as the Northern Lights, what we see as the Aurora Borealis. Give me a smiley face if that makes sense. So when magnetism and electricity mix perfectly, all right, this crazy thing can happen, and it's a really cool phenomena. Awesome. All right, so what I want you guys to go ahead and do, go ahead, everybody type on the whiteboard, what happens when the north pole of one magnet and the south pole of another magnet are adjoined? All right, when they are next to each other, are they going to be attracted? Are they going to be repelled? Are they not going to do anything? Go ahead, tell me on the whiteboard, everybody. Type your answer up there. What happens when a north pole and a south pole are next to each other? Awesome. Let's see who I've got up on the board. I've got Aiden and Jeremiah, Pat, Leslie, Iskari participating. Awesome. Get your answers up there. Got Kanisha on the board, Leslie on the board, Stephen on the board. All right, looking good. Yes. So when a North Pole and a South Pole are next to each other, remember this phrase, opposites attract, right? Here's the phrase, opposites attract. So therefore, that means that they are going to be attracted to each other. What about down here? What happens if a North Pole is next to a North Pole? Go ahead, type your answers up there. What happens when a North Pole is next to a North Pole? Awesome. I see Leslie, Jeremiah. Get your answers up there. Eve is on the board. What happens when a north is next to north? Thank you, Stephen. Looking good, looking good. I see Pat is moving his answer. There we go. Love it. Oof. Yes, you guys are correct. If opposites attract, then you are correct. Likes will repel. So since a North Pole and a North Pole are alike, then they are going to repel. Give me a smiley face if you feel good about that. Okay. Opposites, north and south, will attract. Likes, north and north, or south and south, will repel. Excellent. Looking good. Let's go ahead and keep on moving. Now, magnets, again, they are all about what's happening to their electrons inside of the material, okay? So most of the time, electrons are spinning in random directions. And if that happens, it's not a magnetic material, okay? It's just a regular material like, for example, aluminum is not going to attract other metals, all right, just because the electrons are not lined up correctly or spinning correctly. However, once a material has all of its electrons spinning in the same direction, because again, it's all related back to electrons, then it's going to be magnetic. And what this can actually do is magnets are so strong that they can actually cause other materials to also align their electrons and push them in one direction, even temporarily, so that allows you to actually attract other metals, right? So that's why a magnet can pick up a bunch of paper clips. Even though the paper clips themselves are not magnetic, all right, the magnet is able to take the electrons and affect the electrons inside of the paper clips. Okay, but again, here's the crazy thing, guys. Electricity and magnetism are related. Okay, so what actually happens here is you can actually create electricity with just a magnet and an electric wire, or and a wire. Okay. Yes, it's very attracting. Okay, so you actually don't even need a battery to create electricity. You can actually create electricity with just a magnet and a wire. All right, so I'm going to go ahead and show you what this looks like. All right, so let me go ahead and share this with you. This is going to be underneath your additional reading materials, which you always have access to. I don't know how many of you take a look at them, but there are some interesting things in there. So let me go ahead and show this to you. All right, let's take a look at this. All right, so electricity and magnetism. All right, here we go. Okay, so I'm going to go ahead and zoom into this. All right, and what I want you to see is what happens to the voltmeter, which is measuring electricity, as the magnet passes through this coil. All right, watch what happens down here. What's happening to the voltmeter, which is measuring electricity? Tell me in the chat box. What do you see happening? I can replay that. Take a look at our voltmeter here. I know it's a little bit laggy, but you should still be able to see something's kind of happening. Yeah, your voltage actually goes up. So again, there is no battery here, or there is no outlet here. All that's happening is literally a wire by itself with a magnet going through a coil of wire can actually create electricity. Give me a smiley face if you're beginning to understand that because magnetism and electricity are so related, one type can actually cause another type. Even without a battery. You don't need a battery to have electricity. Okay? So I guess maybe you could charge your phone with a magnet and a wire if you were really willing to pass it through the wire a lot. Okay? All right, so what's really happening is we're taking mechanical energy, which is the motion of the magnet, and we're actually turning it into electrical energy. So again, they are related. Okay? Now, we should know this term already, right? We've learned about conductors and insulators before, but before we were talking specifically about heat. Now we're going to talk about electricity. So we still use these terms for electricity because electricity and heat are actually also related to each other, but for now we're going to go ahead and kind of think of them a little bit separately, okay? So electric currents can flow freely in a conductor, but they cannot flow freely in an insulator. So a conductor will transmit or move electrons, okay, allowing those electrons to flow through, okay? Insulators, though, are going to inhibit or prevent the flow of electrons. Okay, so that being said, metals are very good conductors, all right, which is why we use a lot of metals to carry electricity, and non-metals are very good insulators. Okay, so let's think about this, for example. What is the inside of your charging cord for your phone made up of? What is the inside of your charging cord for your phone made up of? Yeah, it's made up of a metal, specifically, I think Geron's got it. Yeah, specifically it's made up of copper wire, exactly. However, okay, what would happen if we were charging our phone and we just had copper wire going to our phone and we grabbed that copper wire? Tell me in the chat box, what happened if we grabbed that copper wire with our bare hands as it was plugged into the wall? You would get electrocuted, right? Which is not good. So instead, so that we don't get electrocuted, what is around that wire? Think about a lot of your cords are white or black. What is around the wire to prevent you from getting electrocuted? Yeah, rubber or plastic, right? I think it's a combo of both. I don't actually know the material that's making it up, but it is an insulator, okay? So it's made up of plastic or it's made up of rubber, and so the result is that you don't actually get shocked even though it's still able to carry a charge to your phone. Smiley faces if that makes sense. That's why we need both materials, and that's why you should not touch bare wires that are attached to the outlet. I don't know, Junie. You will take a look at it in a few moments, okay? Now, that being said, let's imagine that you are in a lightning storm, okay? Where is the best place to be in a lightning storm, okay? If you are outside, where's the best place to go in order to hide, okay? If you can't get into a house, don't go into a pool. Don't go under a tree. There is actually something metal that you can get into that will actually protect you, but it's not because it's made of metal. What can you get into if you're not by your house that will protect you from a lightning storm? I think Pat's onto something. No, not the ground. Okay, so yes, the thing that you can actually get into is your car. So here's the problem, guys. Remember that you are actually an electrical being. So the reason that you are alive right now is because your heart is beating with electricity and your brain is using electricity, okay? Yes, you are a transformer robot in disguise. Exactly. That's exactly what I'm telling you right now. Okay, so you are made up of electricity, okay? So that being said, or you work because of electricity. So that being said, the reason that a lightning storm can kill you, or a lightning strike can kill you, is because if lightning travels through your body and into the ground, all right, it's going to short out all of your circuits and kill you, okay? However, if you can prevent that lightning from going all the way through you, okay, from actually traveling all the way through your body, then it won't kill you. So the reason that cars work is because the metal part is not touching the ground. What is between the car and the ground? What is actually touching the ground from the car? Yes, the tire. And what are tires made up of? They are made up of rubber, exactly. So what happens is the lightning goes into your body, but it can't actually get through your body because the rubber in the car is preventing it from going into the ground. And so it's able to not harm you because it doesn't actually connect to the ground and pass through you. Give me a smiley face if that makes sense. That is the bad part about lightning, is if it actually passes through your body. Cool. All right. Awesome, guys. Okay, let's go ahead and match these up. Use your whiteboard tools. Match them up on the whiteboard. We got conductor, insulators, current, and magnet. All right, can I give you about 10 more seconds? Let's see who I've got on the board. Thank you, Stephen, Aiden, Dion, Jeremiah, Pat, Leslie, Ascari, Matt. Let's see here. Who else do I got up there? Eve, thank you. Looking good. All right, gonna go ahead and pause your tools now. Let's go ahead, shrink these down. This is going to be number 3 in your ticket. There you go, Junie. This is number 3. All right, so conductor, yes, this is a material that transmits the flow of electric charge. Exactly. An insulator is a material that inhibits or stops the flow of electric charge. Current is the movement of electric charge in general, right? And magnet is a substance that produces a magnetic field. Excellent. This is number 3 in your ticket. Give me a green check when you have it saved. You have 30 seconds. Go, go, go. All right, guys, waiting on a few more green checks. Addie, Akshat, Alex, Amir, Angie, Tony, Ben, Ashley, Deavion, Dion, Manny, Grant, Jacob, Jeremy, Jaron, Juan, Jay, Carrie, Kian, Lindsay, Mia, Mitch, Morgan, Noah, Sarah, and Sid. Moving on in 5 seconds. All right, here we go. All right, guys, so again, electricity and magnetism are related to each other. So this is a really cool thing. Electromagnets are magnets that are made using electricity. So electromagnets create a magnetic field when an electric current flows through a wire that is coiled around a metal core. So the coil is what's really important, okay? So what happens here is that you can actually use electricity to create magnetism, right? So we just talked earlier about how passing a magnet through a coil can create electricity. Now, having a coil of wire with electricity can actually create a magnet. Give me a smiley face if you're starting to understand those connections, okay? So this is really important because the cool thing about electromagnets is you can actually turn them on and off, okay? Because how many of you guys have ever seen in TV those big magnets that can pick up cars? Those gigantic magnets that can pick up cars. Okay, now if those gigantic magnets were real magnets, then it would pick up a car and it would never get off of the car again, right? If those are real magnets, okay, normal magnets, it would never be, yeah, so Dion, these are all types of electromagnetic forces. Yeah, so that car would never leave that. But instead, if that magnet is actually made from electricity, then you can just turn off the electricity and then the car will drop off of the magnet. Okay, so I'm going to actually go ahead and show you what this looks like. All right, so maybe, here we go. So this is an electromagnet that I have. I've got a core of a iron nail, and around it there's a coil wrapped a bunch of copper. Okay, so copper wire wrapped around it. Okay, and I'm going to go ahead and I'm going to actually attach it to a battery here. Okay, so it's a really big battery, so I'm not going to actually have it attached long because it gets very hot. And I'm going to actually show you how it can actually attract some paper clips. Okay, so let me go ahead. I'm going to set this up really quick. Put this in here. Awesome. Get this ready to go. And let's take a look at this, okay? So take a look at this, all right? We've got our magnets, our paper clips. And currently, is this magnetized? Is it actually picking up any of the magnets? No, because it's not, it has no electricity yet, okay? So by itself, this is not a magnet. By itself, it's not a magnet. But now I'm going to go ahead and attach the other side to the battery. And now take a look at this, and I'm going to try not to electrocute myself. Now, what do you guys see? What do you guys see now? Yes, as soon as both sides were attached to the battery, it can actually pick up paper clips. But again, as soon as I detach this, hold on, I'm going to hold this in my mouth. As soon as I detached it, what happened to all the paper clips? Except that last one. What happened to all the paper clips as soon as I detached it? Yeah, they actually fell down, guys. Okay, so again, electricity can be used in order to create a magnet. And the cool thing is the more coils you get, the stronger this magnet gets, which is why we can actually create very, very strong magnets for much cheaper than it would be to make the same type of magnet from real magnetic materials. Give me a smiley face if you understand that. A real magnet this size would be crazy expensive, but getting a bunch of coiled wire is not that expensive. Awesome. Okay, so we'll talk about this a little bit later, but really what's happening here is that anytime you have an electric current, you're actually creating a tiny magnetic field around it as well. But it's very, very weak, which is why we don't usually notice that it's magnetized when we just are charging our phone, for example. But what happens is once you start to coil that wire together, it begins to bring all of those little magnetic fields in line with each other to create a much larger magnetic field. And if you put some iron or you put a metal core in the center of it, this has a even bigger effect at aligning this magnetic field, allowing us to create an actual magnet with just a battery or with just electricity. Thumbs up if you understand. I know, so I'm so sorry, Askari. I'm going to finish us up here in a moment. Awesome, guys. Okay. So we're going to actually talk about electric motors during our lab, so I'm going to go ahead and skip this for now. Just know electric motors also are the interaction between electricity and magnetism, which is the whole theme of today. All right, so let me go ahead and give you guys your quiz really quickly. Here is the link to your quiz, everyone. Awesome. Make sure you do it with your attendance tickets, submit them at the same time. And then here you go. Here's your last word. Have a great day, everyone, and I will see you after spring break because we don't have class tomorrow. Bye, everyone.